Hello everyone, welcome to the fourth installment of our OrangePi beginner tutorial. Before we dive in, let me introduce our discussion group. In this group, I'll help you solve various problems within my capabilities. I hope everyone will join the group for discussions. Previously, I covered the basic environment setup for the OrangePi. Now, let me outline the upcoming schedule. My first planned project is to build a simple line-following car using the OrangePi. As competition challenges grow increasingly complex, line-following robots have become an essential entry-level project for competitions. Through this straightforward project, we'll teach you fundamental Raspberry Pi functionalities like GPIO, I superscript 2C, PWM, and camera integration. My goal is for you to not only build your own line-following robot after watching these videos, but also to leverage these foundational skills to create your own innovative projects. The second plan is to build upon our completed line-following car, and then add object detection and recognition capabilities. This functionality will be achieved using the YOLO deep learning model. At that stage, we'll teach you how to train and deploy our deep learning model. Of course, these are preliminary plans, and may be adjusted based on actual circumstances later. Now, let's take the first step with the line-following car. Using GPIO to light up an LED, our goal is to make the LED strip light up for 2 seconds, then turn off. After another 2 seconds, it turns on again. This cycle repeats continuously. Here's the list of components we'll use this session. First, we need 2 male-to-female DuPont cables. Second, we need a 5V LED strip like this. Zooming in reveals. The strip consists of repeated small modules. Abstracted, the circuit looks like this. A power source supplies the LEDs. The resistor acts as a voltage divider and current limiter. Current limiting prevents excessive current through the LEDs. Voltage division ensures the voltage across the LEDs doesn't exceed their maximum tolerance, preventing burnout. Finally, ground the circuit to form a closed loop. Correspondingly, this is where we connect the power supply. This component is the resistor we mentioned. The illuminated section here is the light-emitting diode, LED. And this final point connects to our ground wire. Observant students will notice it's labeled 5V. This 5V rating means it can handle a maximum input voltage of 5 volts. Exceeding 5V could potentially burn out the light strip. If we input 3.3V here, the brightness might be slightly dimmer, but it will still illuminate normally. Now let's discuss the classification of DuPont wires. The male end of a DuPont wire refers to the pin-equipped side, while the female end refers to the hole-equipped side. Therefore, DuPont wires can be categorized into 3 types based on their male/female ends. One type has both ends as male connectors. This is called a male-to-male DuPont wire. A male-to-female DuPont wire has one male end, and the other end has a female connector. Female-to-female DuPont wires refer to those with female connectors on both ends. These female-to-female DuPont wires will be used very frequently later on, because DuPont wires are designed to be plugged together for use. Well, that's the reason. Alright, let's formally discuss GPIO. GPIO stands for General Purpose Input, Output Port, commonly abbreviated as I/O ports. We typically use header pins to bring out the GPIO pins, which are then referred to as pins. We can use DuPont wires to connect GPIO pins to other devices, enabling the output of signals to other devices, or the reception of signals from other devices. As you can see in the image, this location represents our GPIO pins. Later, we'll connect peripherals to these pins for use. As mentioned earlier, GPIO can receive or output signals. In the OrangePi, signals are represented by high and low levels. What do these levels mean? For the OrangePi's GPIO, a high level refers to 3.3 volts, while a low level refers to 0 volts. This is because GPIO can only output voltages of 3.3 volts or 0 volts. It has only these two states. We call 3.3 volts a high-level state, and 0 volts as a low-level state. Furthermore, the GPIO operates in two modes, output mode and input mode. Of course, both modes have numerous related subtypes, which we'll cover in future sessions. In output mode, as mentioned earlier, GPIO can only output two voltage states. We can supply a high level to an LED to illuminate it. Later, we'll also use GPIO to control PWM output. In input mode, GPIO can read the voltage levels from external devices. For instance, it can detect whether an external input is high or low. This enables the implementation of related functions. In this session, we primarily utilize the output functionality of GPIO to achieve our LED lighting operation. Here is the circuit diagram for the LED we mentioned earlier. The GPIO here functions as a power source. When GPIO outputs a low level, i.e. 0 volts, it effectively acts as a 0-volt power supply. Thus, the LED remains off. If the GPIO outputs a high level, it provides a 3.3-volt power supply. Although the brightness is slightly dimmer, it still illuminates our LED. Now let's discuss some special cases. This time, we've added a multimeter to the circuit. To measure the voltage across the LED terminals, we've specified a red LED for this experiment. As we can see, this red LED has a normal operating voltage of 1.8 to 2.2 volts. In our circuit, the measured voltage across it is 1.81 volts, so it can operate normally. If we remove this resistor, we see the voltage now directly reaches 3.3 volts. This exceeds the red LED's tolerance voltage of 2.2 volts, causing the LED to burn out. This demonstrates the resistor's function. It provides voltage division. If you're using a single LED rather than a strip, you must always connect an external resistor. This effectively prevents the LED from burning out. We should add that an LED's voltage tolerance relates to its color. It increases in this order: red, orange, yellow, green, cyan, blue, violet. This is because different frequencies of light require varying amounts of energy to excite. Higher frequency light demands more energy for excitation. Therefore, during design, its voltage tolerance is set higher. If you want to understand the deeper reasons, then look into semiconductor physics. Purple and blue LEDs typically have slightly higher voltage ratings. For a purple LED, the voltage rating is around 3.3 volts. Connecting it directly to a circuit might work, but the current could exceed its operating limit. Adding a resistor is absolutely essential. Searching for GPIO in the OrangePi manual reveals this diagram. This shows pin numbers 1, 2, 3, 4, 5, 6, all the way to 40. These correspond to the 40 pins on the OrangePi. You'll notice each pin has a designated name. For example, pin 1 is labeled 3.3V, meaning it can consistently output 3.3 volts. Similarly, pin 2 is named 5V, indicating its output voltage is always 5 volts. Other pins have different functions. Pin 9 is labeled GND, short for ground, meaning it connects to ground and corresponds to 0 volts. Various other names represent different functions, which we'll cover later. This column and that column show the internal GPIO pin numbers within the OrangePi chip. You can see pins 1, 2, 4, 9, etc. But their GPIO functions are undefined, meaning these pins lack GPIO functionality. Moreover, among the predefined GPIOs, their pin numbers don't match our pin numbering. This means later, when configuring the file, we need to perform an operation to map pin numbers to GPIO numbers. This will be covered later in the video. This section displays the current GPIO operating mode. They're all set to input mode by default. Of course, we can also set it to output mode. Alright, having covered all that, let's move into the hands-on session. We'll now use the PiCharm we installed last time to operate the GPIO, making our LED strip light up for 2 seconds, and then turn off for 2 seconds. For PiCharm to directly control the GPIO, it requires elevated privileges. We'll log into our system directly as the root user. Open the terminal and enter this command line. After entering your password, press enter. Then reboot the system. You can now log in as the root user. After rebooting, you'll notice the name in the top right corner has changed to root, indicating you're now logged in as the root user. We also need to install a package called OPI in the system's Python environment. This package contains numerous functions that make it easy to operate the GPIO. Enter this command in the terminal to download the package. Once downloaded, we must modify the package's configuration file to map GPIO numbers to our pin numbers. This ensures pins correspond to the correct GPIOs. When running programs later, this configuration file is typically located at the path shown in the subtitles. We need to locate and edit it. For convenience, we'll open it using pycharm. After opening pycharm, we need to modify the section highlighted in the dotted box. The left column lists the pin numbers with GPIO functionality. We must change the right column to match these pins with their corresponding GPIO numbers. Currently, the mappings are clearly incorrect. You can cross-reference the GPIO diagram in the manual. Make the necessary adjustments yourself, or refer to the code I've already written here. The middle section contains the code for the 5P board, while the right side shows the code for the 3B board. Once you've finished writing, simply save it. Next, create a new Python file to write our LED lighting code. Here, we first import the GPIO library we downloaded earlier. Then, we import the sleep function from the time module to help us implement a delay later. The following line of code, GPIO.setMode, specifies the mode defined on the board. This mode means GPIO is initialized in the default manner. We will use pin 3 here. We need to configure pin 3 to initialize it in output mode. Therefore, we will use the GPIO.setup method. The first parameter inside the parentheses is the pin number we need. The second parameter configures the operating mode of that pin. Next, we need to write an infinite loop using while true. Those familiar with microcontrollers know. This infinite loop keeps the code running continuously until manually stopped or power is cut, at which point the program terminates. Within this loop, we primarily use the GPIO.output method to configure the GPIO output mode. The first parameter is our pin number. The second parameter specifies whether the GPIO should output a high or low level. Writing GPIO.high outputs a high level. GPIO.low outputs a low level. Then, between these two lines of code, we write the sleep delay function. We set it to a 2-second delay. This way, the GPIO can output a high level for 2 seconds, and then output a low level for 2 seconds. Finally, we use print to display the high and low levels. To observe the code's execution on the computer. After writing the code, connect the LED strip's positive terminal to pin 3, and the negative terminal to GND. Once wired, click the Run button to achieve the effect shown in the video.